We've learned how to solve differential equations with constant coefficients that are homogeneous. That is, that are in this form that you see here, with the g of x being equal to 0. Now we're going to take a look at the non-homogeneous linear differential equations with constant coefficients. So we're still in the domain of constant coefficients, but this time we have a non-homogeneous differential equation. And the method that we're going to take a look at is called the undetermined coefficients. And there are two approaches to undetermined coefficients. It's the same method, it's just a different approach. One is called the superposition approach, and the other one is called the annihilator approach, and we'll look at both of them. So here's a breakdown of the steps that are part of this method of undetermined coefficients. So we're going to have the following strategy. Step 1, we'll find the complementary function yc by solving the associated homogeneous equation. Okay? The associated homogeneous equation is just taking this equation and setting g of x equal to 0. And how will we solve that? Well, it's a linear differential equation with constant coefficients, so we'll do this using the auxiliary equation as we've done before for the homogeneous equations. And at first it might seem odd that we're considering the associated homogeneous equation, but remember that the general solution to a non-homogeneous equation is composed of the complementary function, which includes the solutions to the homogeneous equation, and one particular solution. And any particular solutions differ by solutions to the associated homogeneous equation. We learned that during the as we were learning the theory for linear equations. Okay, so that's the first part, is to get the complementary function by solving the auxiliary equation. Then we're going to find a particular solution, any particular solution. And remember that with a particular solution, we actually get a solution that, on the right-hand side will respect this g of x. Okay, we could always add zeros, right, to g of x, and that's why we, solutions, particular solutions differ by solutions to the associated homogeneous equation. But all we need to do is just find one particular solution. Then the general solution will be y complementary plus the particular solution. And the final step, and this only applies if we're looking at an initial value problem or a boundary value problem, is that we'll take this general solution and apply the initial condition or boundary condition to it. Okay, and it's important that we consider the general solution that we apply the conditions to, and not just looking at the complementary or particular solution. So let's start with an example. Here we want to solve this non-homogeneous equation. Is it linear? Yes. Are there constant coefficients? Yes. So we're in the domain that we're applying the method of undetermined coefficients to. Okay? And so the associated homogeneous equation is what you see here. And it has the auxiliary equation m squared plus 4m minus 2. Okay, you just take the coefficients, and y prime is associated with m, and we've done a lot of this when we discussed solving homogeneous equations with constant coefficients, linear homogeneous equations with constant coefficients. And we apply the quadratic equation. Okay, we get these two solutions there. They're real, they're distinct, and so we're left with this complementary function. Okay, so the general solution of the associated homogeneous equation is called the complementary function. It's not the general solution of the whole differential equation, but just of the associated homogeneous equation. Step 2, now we want to find the particular solution. Well, how do we do that? Okay, we need to satisfy this differential equation. And if you take a look, the right-hand side is a polynomial, 2x squared minus 3x plus 6. So why don't we do this? Why don't we just guess the general form of how a particular solution would look like? Let's make a guess, okay? And this is not totally crazy, right? We know that if we take derivatives of a polynomial, we get another polynomial. And on the left-hand side there, we have a chance of, applying this particular solution to the left-hand side and matching it to the right-hand side. So what we're going to do is make this educated guess. Okay, we're going to say that, let's assume the particular solution has this form. Okay, so its derivative will look like this. You just take the derivative. Here, a, b, and c are just constants. Okay, constants that we want to determine. These are the undetermined coefficients. And the second derivative looks like that. Well, we're now going to impose equality, right? We have the left here, that's given, that's from the problem, okay? So that's in pink there. And we ask this question, can we make this work? Okay, and can we make what work? Well, this equality where the right-hand side now is this guess applied to the differential equation, okay? And so we leave it as a question mark. We're hoping that we can make this work. And so in blue here, you'll see, here's the second derivative, 2a, so it shows up there. For the first derivative, that's here, and so on. So we just apply our guess to the differential equation, and now we have this right-hand side and this left-hand side. And our next line here, we just get, we just apply these to the extremes of the left and right equal to each other. And now we have a 2 in front of the x squared. On the right-hand side, we have a negative 2a. If the left-hand side is going to equal the right-hand side, well, the coefficients of each ordered term in this polynomial, right, better be equal to each other. So this has to be, this negative 2a has to be equal to 2. 8a minus 2b has to be equal to negative 3. And likewise, in green, you see that 6 has to equal this expression here. And so in orange, we write that condition here, and we solve and we get a must be equal to negative 1. We take the blue here, and we get this equation, and we could actually solve this, and since we have a there, we could solve this, and we get negative 5/2. And finally, the just term that's not multiplied by x, or if you will, x to the power of 0, which is just 1, okay, gives us this. Okay, so notice that we're matching the coefficients for each term, x squared, and x to the power of 0, or 1. And we get that c must equal -9. And so we were able to satisfy this equality. We succeeded in satisfying this equality. And we did have to solve a system of 3 algebraic equations for 3 unknowns, a, b, and c. But we were able to consistently solve. And we go back to our initial form there. But this time we do know that a must be equal to -1, b minus 5/2, and c -9. And so the general solution then, the last step here, is that y is equal to the complementary function plus the particular solution. So here's our complementary function from step 1 that we had up here. And here's our particular solution. And so this is the general solution. Any solution can be determined by this general solution by just fixing the constants. So some quick remarks here. The method of undetermined coefficients works because the coefficients AI are constant. Okay, the coefficients in the linear differential equation that we're considering. Okay, that's very important because you could see that we were able to guess this polynomial because the differential equation is not going to change the properties. If there was a e to the x over here, well then it's going to get much more complicated. You're not just going to be able to guess a form because you have coefficients that will change that form. Okay, constant coefficients, on the other hand, just take the form and multiply it by constants. Derivatives here also for polynomials will give you another polynomial, or for example for exponentials or sines have a cyclical nature to them. Okay, and that's important because we want to somehow match the left-hand side and the right-hand side. So first remark, constant coefficient. Second remark, g of x has the property that repeated differentiations yield a finite amount of forms. Okay, so basically g of x must be a constant or a polynomial or an exponential function or a sine cosine function or finite sums and products of these functions. Okay, so we have an exponential times a sine, we could still make a guess. Okay, if we have a polynomial times an exponential times a sine or cosine, still works. Okay, but we're limited to sums and products of these. Okay, if on the right hand side g of x is equal to arctan of x, okay, it's not going to work. It won't work out for us because its derivative doesn't have this cyclical nature. Okay, so that won't work. And here are examples of functions g of x and the guesses that we would make. Okay, so here we just take concrete examples of g of x and we show the form that one should guess. Okay, the form that one should guess for the particular solution. So if we have a 1 or any constant for that matter, we'll take a guess that yp is equal to just a constant a, and then do as we've done above and solve for a. What about 5x plus 7? We'll take the guess ax plus b. What about this one, 3x squared minus 2? Now naively you might think ax squared plus like b, but that's not the case. Okay, yes, there isn't a term that's that has a power of x in there, right? Or you could say it's 0 times x. But we still have to include that here in our guess. Okay, so that's very important. X cubed, again, we don't have an x squared term in here, but we're still going to include a term with the x squared. Okay, again, when you were taking derivatives, different things mix up. We're taking derivatives in the differential equation, adding it together, so we can't be presumptive here and say, since x squared doesn't show over here, we're not going to include that there. Okay. Sine 4x, well, again, sines and cosines are oscillating in terms of when you differentiate, so you have to include both. Okay, so we'll have a coefficient a with cosine 4x. We know that since this has a 4 in there, we know that the 4 has to also be in the sine and cosine. Okay, you're not going to be able to take derivatives of cosine 3x and somehow match them to a sine of 4x. Okay, you can't take derivative of cosine and match that to a sine. This sine over here could match with that sine. And the problem now is to just determine a and b. Well, what about cosine 4x? Same as sine of 4x. Okay, so you always include, even if they don't show up there. If you have a sine 4x plus cosine 4x, well, you'll still make this guess here. This also works for exponentials. You'll make the guess that it's equal to a e to the 5x. Again, notice that we still are going to respect that 5 there. Taking derivatives of e to the 6x is never going to match that e to the 5x. What about products of, say, a polynomial and an exponential? Well, we'll take a product of a polynomial and exponential. X squared e to the 5x, again, the x and constant term don't show up there, but we still include them in our guess. Exponential times a sine, well, we're going to then have terms that look like this for our guess, okay? A polynomial times a sine. Here, be careful, right? So you'll have a polynomial multiplying the cosine term, and you'll have a polynomial of the same order, right? Since this maximum here is x squared, so we'll include, another term here multiplying the sine 4x. Okay, and notice here is sine 4x. We have a cosine 4x. What about a polynomial times an exponential times a cosine or sine? Well, you'll have this form here in this case. Okay, where of course the polynomial goes up to the highest order. Here it's just x to the 1. If it was x squared, we'd need a x squared term here and x squared term over here in this parentheses. So by looking at this table, rather than just writing out, this kind of algorithm, you get an idea of what kind of form you should guess, okay? Now, it might be the case that, you don't just get a cosine 4x for g of x. You might get a cosine 4x plus e to the 5x, okay? And that's different than this, right? This is a product, e to the 3x times sine 4x. You might instead get cosine 4x plus e to the 5x plus, say, a term that's the product, okay? Then what do? Well, let's remember the superposition principle for non-homogeneous equations that we've discussed when we were talking about the theory of linear equations. And it goes like this: if ypi, okay, this is like a subscript of a subscript, is a particular solution of this non-homogeneous equation with this g sub I, okay, so this ypi is a particular solution that corresponds to this differential equation where gi is used on the right-hand side, then yp equal to c1 yp1 plus c2 yp2 plus ck ypk is a particular solution of this non-homogeneous differential equation, okay? So what does that mean? That means you could solve this piecemeal. You could just consider, you could just ignore these terms and do what we did above with just this first term, and then you get your C1 YPI, okay? Or say, look at it this way, okay? And this C just shows you that, just as you could add linear, you could also multiply by constants, okay? And then you could consider this, and you could even ignore the constant if you want, although that's not too helpful. And then just solve the differential equation with that, and then that your particular solution will be this term here. And then you just sum all of them at the end, okay? It just means you could ignore the others while you solve for one term in here, and then just sum at the end. Okay, so we may use the proposed form for each GI, then use the superposition principle. Now, this is very important, so we have to pay very close attention to this remark. It may be the case that a conjectured form for yp is a solution of the associated homogeneous equation. Thus, we will consider case 1 where this doesn't occur and case 2 where it does, okay? So what does that mean? That means that, say on the right-hand side we have this e to the 5x, but in the complementary function, we also have an e to the 5x. So then we know that when we plug that form into the differential equation, we're going to get 0 on the right-hand side, not g of x, and so we're not getting a particular solution. Now we're going to tackle that situation later. For now, we're just going to consider the case where that doesn't happen, okay? And in part 2, we will consider the case where it does. So this is case 1. No function in the assumed particular solution is a solution of the associated homogeneous differential equation. Okay, so this problem does not happen where you make a form for yp according to the rules, the examples that you see above, and it turns out to be in the complementary function. So form rule for case 1, the form of yp is a linear combination of all linearly independent functions that are generated by repeated differentiation of gx, okay? And that's just basically combining here the superposition principle and the examples that we saw above, okay? So it's a linear combination of linearly independent functions. This is meaning each particular solution here corresponding to each term in the sum on the right-hand side. Okay. And this is just basically telling you here that the form needs to respect that the derivatives are somewhat cyclical, okay? And what I mean by that is the forms repeat, okay, in a sense. Of course, if you take the derivative of x squared, you get 2x, right? And you keep taking derivatives, you're going to eventually get 0. So that's not what I mean by cyclical, okay? Even though cosine and sine do have that cyclical property, the exponential also has that kind of cyclical property. But here I just mean that they retain somewhat of a same form, okay? And that's what that means there. So determine the form of a particular solution of the differential equation we see here. Now, previously, we solved completely the differential equation. We got a general solution, okay? Now we're just asking for the particular solution, okay? Just determining the form, right? Not actually solving the whole differential equation. So we have this 3x squared term. What does that need? That needs a y particular that looks like this, okay? So this we're going to call that g1, 3x squared, and it's going to contribute to the particular solution, this yp1, all right, that has this assumed form because it's x squared. We're going to look at this and we're going to call this g2 of x, okay? And what particular solution form should we guess for that? Well, we're going to say yp2 is equal to e cosine 2x f sine 2x, okay? And finally, g3, 8x e to the 6x, we're going to guess a form here that corresponds to this, okay? So y particular here has that form. And let's just check that we're actually in case 1, okay? Note that the auxiliary equation, okay, for this differential equation could be factored, okay? And you have this complementary function. Now, take a look. This is a polynomial. It's not the exponential. This is an exponential, but look at that 6 there. That doesn't show up here, okay? So we are in case 1. None of these linear terms corresponds to anything that could be part of the complementary function. Because none of the associated particular solutions are solutions of the associated homogeneous equation, we have that y particular, we should guess this, okay? And now you could see why, we're just asking for the form of the particular solution and not actually solving it, because we have 1, 2, 3, 4, 5, 6, 7 unknowns, okay? 7 equations, 7 unknowns. And so it'll take many pages or a lot of lines to solve that. We have seen how to actually solve these in the previous example Here we're just working on the form. So one may find ABC independent of EF, independent of GH. What does that mean? That means that what you could do is just take this and do what we did in the previous example and solve for ABC, okay? So what you'll do is take this and just this, ignore these, and solve for ABC. And then take this and ignore these other two and just take that, okay? And do what we did in the previous example and solve for EF. And similarly for the GH, you just keep this and this, and you know, you ignore these. You just remove them and solve for GH. So you could solve these independently, okay? Or you could actually take this whole term and just plug it into the differential equation, and then you'll also have that right-hand side, okay? This works because of the superposition principle, all right? These terms are actually end up, so these are only going to be matched with coefficients here. This is only going to be matched with coefficients from this guy. And so we're only going to match coefficients of these terms using this guy. And we're only going to match coefficients of this guy using this guy, okay? So no need to, so you know, you could just solve these independently, or you could solve them all together. It's just what your preference is really, okay? And just to kind of make that point clearer, here's what I mean by that. So, for example, you could just solve y double prime minus 9y prime and then just take yp1 and plug that, you know, plug it into the differential equation and match terms as we've done in the previous example, and then do the same thing with the other terms. Or you just take this whole differential equation that you see here and not ignore the other terms. So you take 3x squared minus 5 sine 2x plus 8x e to the 6x, and you plug in this whole thing into this here. Both of them work. So let's consider one more example. Okay. So we want to solve this. Okay, this is now a third order differential equation, but it's okay. The same principles work. We start with the auxiliary equation. Here it is. This gives us a repeated root, m equals 0 with multiplicity 2, and m equals minus 1. Okay, it's a little bit unclear here. That's just the m is equal to minus. That's the second solution. And so for the repeated root, we know what to do from our studies of the homogeneous equation. We just multiply by x there. The m equals 0, you know, is in here, and that's just 1, right? And so in this term here corresponds to the m equals minus 1. So we get this complementary function. Now for a particular solution, we're going to guess a form that respects this form, okay? An exponential times the cosine. Now a sign doesn't show here, but we still include as discussed above. And now we have this term here. This is coming from what's given in the problem. And then on the right hand side, we take this and plug it into the differential equation to get the right hand side here, okay? And we match terms, so this negative 2a plus 4b, well, that's in front of the ex cosine x, so it needs to equal 1, and that's what you're seeing there. And this term here, well, there is no e to the x sine x on the left, and so that's a 0, okay? And so we have that relation there. Solving for a and b, we get this, and our particular solution is then this. And so our general solution is the complementary function plus a particular solution, and so we get this general solution there.